Welcome to the Deep Dive. We're here to unpack complex research and give you the essential insights. Today, we're looking at a really big paradox right at the heart of the energy transition. Copper. I mean, we know we need it, right? Copper is basically the backbone of electrification. Our sources show that things like wind and solar PV, they need way more copper per megawatt than the old fossil fuel tech. So we're building this clean future, but it demands just massive amounts of this one metal.
That's exactly it. But here's the catch, the really big problem I have to figure out. Making copper right now uses a ton of energy, a ton of water, and creates a lot of emissions. And it's getting worse, actually. The quality of copper ore is going down worldwide, so miners have to dig up and process more rock.
Just to get the same amount of copper.
Right, which pushes the energy demand per ton way up. Some forecasts are frankly pretty sobering. They suggest copper production alone might need something like 2.4% of all global energy by 2050.
Wow.
Yeah, so if we're serious about decarbonizing, we absolutely cannot let the supply chain for our clean tech become this huge energy hog and pollution source.
Okay, so that really sets up the mission for this deep dive, doesn't it? We're diving into a specific study, an optimization study, that asks this fundamental question, especially for dry mining areas. Can we actually cut copper production completely off from fossil fuels and fresh water? Like, can we make it 100% renewable and use zero fresh water?
And the study that tackles this head-on is titled Integration of Seawater, Pumped Storage, and Desalination in Multi-Energy Systems Planning. The case of copper as a key material for the energy transition.
That's quite a title. So for you listening, the goal here is to get your head around how these integrated renewable systems, specifically using seawater, could make one of our most resource-hungry industries cleaner and, crucially, cheaper, too.
That's the target. 100% renewables, zero fresh water.
All right, let's start with the approach this study took, because normally energy and water planning for mines are kind of separate things, right? Buy power, buy fuel, get water.
Exactly. Yeah. But this study did something new. It used a multi-vector approach. It looked at designing the desalinated water supply and the energy supply together, considering all the energy needed.
All the energy, so not just electricity.
No, everything. Electricity for the big machines, sure, but also heat for processes like smelting, and even fuels for things like haul trucks. The whole energy picture integrated.
That sounds way more complex.
It is, but it's necessary. And the core technical idea that makes it feasible is this thing they call IPHRO.
IPHRO, okay, what's that stand for?
Integrated Pumped Hydro Reverse Osmosis. And what's really innovative here is that it's the first time this kind of combined desalination and pumped hydro storage idea has been put endogenously into a planning model.
Okay, hold on. Endogenously. That sounds important but technical. What does that actually mean in practice?
Right. So think of it like this. Planning exogenously is when you decide first, okay, I need solar panels and a battery. You tell the model what to build. Playing endogenously, like in this study, is different. You give the computer all the options, solar, wind, batteries, gas, this IPHRO thing, and you say, you figure out the absolute cheapest, cleanest system.
Ah, so the model chose IPHRO. It wasn't just assumed to be part of the solution.
Exactly. The model identified it as the cost-optimal choice for providing flexibility.
Yeah.
That makes the finding much stronger.
Okay, got it. So the model likes IPHRO, but what is it? How does it work, especially given the location they studied? This was in Chile, right? The Atacama Desert.
That's right. The world's biggest copper region. Very dry, obviously. They modeled a generic mine there with the system split. You've got the seashore, and then the mine itself 140 kilometers away and way up high, 2,700 meters above sea level.
2,700 meters. That's incredibly high to pump water.
Yeah.
How does IPHRO turn that challenge into an advantage?
Well, that's the clever part. It uses a single pump turbine setup. You pump seawater up to a reservoir at that high altitude, ideally using cheap solar power when it's abundant. Then, when you need either energy or fresh water, you let that seawater flow back down. It can go through the pump turbine, generating electricity to stabilize the grid.
Like a regular pumped hydro battery.
Right. Or it can be diverted to a reverse osmosis desalination plant, the RO plant, to make fresh water.
So it serves two purposes with one flow of water, basically.
Precisely. And it tackles a huge issue for mines and dry areas. Desalination uses a lot of energy. By coupling it with pumped hydro, you can power the RO plant using that stored energy, often from excess solar, smoothing out the demand. It's like a smart battery and a smart water tap rolled into one.
Okay, that makes sense from an energy perspective, but desalination has that other problem, the brine, the super salty wastewater. What does IPHRO do about that? Is there an environmental angle here too?
Yes, and this is really neat. Standard RO plants produce this concentrated brine. If you just dump it back in the ocean, it can really harm marine life near the coast. But with IPHRO, remember that water also flows down just to generate electricity through the turbine.
Yeah, the pumped hydro part.
Well, that generates a massive flow of regular seawater going back into the ocean. The IPHRO design just mixes the small stream of concentrated brine from the RO plant into that huge stream of turbine discharge water.
Ah, so it gets diluted, massively diluted, I imagine.
Hugely.
Yeah.
The study actually calculated it. For their fully renewable scenario in 2030, the amount of water discharged by the turbine was over 14 times the volume of the brine produced.
14 times. Okay, so you're basically neutralizing the brine problem before it even hits the ocean.
Exactly. The environmental solution is baked right into the core infrastructure design. It's a fantastic example of integrated thinking solving multiple problems at once.
That is clever, a real co-benefit. Okay, so IPHRO seems technically smart and environmentally better, but the big question, especially with pumping water 2,700 meters up, does it actually pay off? Is it economical?
Right, that's what they tested. The researchers set up 4 scenarios. S1 and S2 could use existing fossil fuels. S3 and S4 had to be 100% renewable.
And the key difference?
S2 and S4 were the ones where the model was allowed to build IPHRO if it wanted to. S1 and S3 couldn't use it.
Okay, and what did the model decide? Let's talk infrastructure first.
Well, first off, no surprise, given the Atacama location, solar PV was huge in all scenarios, lots of sun there. But here's the clincher. Whenever IPHRO was an option at S2 and S4, the model always chose to build it.
Always. So it consistently saw IPHRO as the best way to get cheap flexibility.
Yes, the essential partner for intermittent solar, basically. And you can see its impact even when fossil fuels are still in the mix. Compare S1, which is just fossil-based, to S2, which adds IPHRO. Even using today's costs, adding IPHRO in S2 allowed the system to get rid of 70% of the natural gas power plant capacity needed in S1.
70% displacement just by adding IPHRO. That's significant, even before going fully renewable.
It shows it's a powerful tool for decarbonization right out of the gate.
Okay, now let's focus on the 100% renewable scenarios, S3 and S4. We see hydrogen popping up here, and lithium-ion batteries too. How did the model figure out the roles for those?
Yeah, that's interesting for the whole multi-vector picture. Hydrogen gets installed, but it's mainly used directly for initiating the smelting process. That needs a flexible, high-temperature fuel source that batteries just can't provide. But for storing electricity and balancing the grid, the model showed lithium-ion batteries become more and more important over time. They basically edge out hydrogen for pure electricity storage because they're more efficient, better round-trip efficiency.
So batteries for electricity storage, hydrogen for specific fuel needs where batteries don't work. Makes sense.
Right. Using the best tool for the job.
Now, the absolute bottom line. The cost. We know IPHRO involves big infrastructure. Does it make the renewable system way more expensive?
This is the really striking part. The answer is no, not at all. In fact, the fully renewable systems, S3 and S4, their costs were pretty much the same as the conventional fossil systems, S1 and S2, right from the start, back in 2020.
Wow, same cost today, but with zero freshwater use.
Exactly. Already competitive. But here's the kicker. By 2030, S4, that's the 100% renewable system with IPHRO, becomes the absolute least cost option out of all 4.
The cheapest. Cheaper than fossil fuels.
Yes. And it stays the cheapest right through their 2050 projections. IPHRO is what enables the cheap solar power to dominate reliably. It just tips the economics completely in favor of renewables, and quite quickly, too.
Can we put some numbers on that cost reduction?
Yeah, the study projected the specific cost, that's the cost of energy and water per ton of copper produced, would fall from around 520 to 670 euros currently, down to maybe 330 to 360 euros per ton by 2050 in those renewable scenarios.
That's potentially a 40% drop in major operating costs, driven by clean energy. Incredible.
It really is. Cheaper, cleaner, no fresh water needed.
Okay, it sounds almost too good. Let's talk robustness. Did these results hold up when they factored in real-world uncertainties like, construction costs changing or fuel prices going wild?
Good question. Environmentally, S3 and S4 are obviously zero direct emissions, which is great. S2 with IPHRO was also cleaner than S1 because it displaced that gas power early on. But for the economic robustness, yeah, they did a big Monte Carlo simulation. They focused on that key year, 2030, and threw in variations in the costs for the seawater infrastructure, the pipes, the storage, and critically, the volatile prices of natural gas and diesel.
And did the whole thing fall apart?
Not at all. The conclusions held strong. S4, the renewable one with IPHRO, consistently came out with the lowest average cost, but maybe even more importantly, it
Yes.
showed less dispersion in its potential costs compared to the fossil fuel scenarios, S1 and S2.
Less dispersion. Okay, translate that. Why is that such a big deal for a mining company?
Less dispersion means less risk, less uncertainty. The potential range of costs for the renewable system was narrower. Think about it. If you rely on S1 or S2 and the global price of natural gas suddenly spikes, your operating costs could go through the roof. You're exposed to that volatility.
Right. Whereas the renewable system,
Its fuel the sun, the seawater, via IPHRO storage, is essentially free and predictable once the infrastructure is built. So S4 offers cost stability. For a mine needing to operate reliably for decades, that stability is a massive competitive advantage. Investors love that kind of predictability.
that makes perfect sense. Lower risk is almost as good as lower cost.
Definitely. And the simulation also showed that just adding IPHRO to the renewable mix, comparing S4 to S3 without IPHRO, cut total costs by about a fifth initially, and still provided an 8% cost saving out to 2050. IPHRO isn't just feasible, it's actively beneficial for the bottom line and stability.
Okay, so let's sum this up. The tech works, it's cost competitive right now, it's set to be the cheapest option by 2030, it slashes emissions, eliminates freshwater use, and it even reduces financial risk from fuel price swings.
Pretty much, yeah. It's a compelling package.
Were there any limitations noted? Anything the system doesn't solve yet?
Yes, the study authors were clear about one key area for future work. They found that in their model, the water pipes and the desalination plant itself were sized pretty close to the mine's actual water demand, maybe only oversized by like 1.5%.
Meaning?
Meaning that while the energy supply side became super flexible thanks to solar and IPHRO, the water demand side wasn't really offering much flexibility back to the system. The mine just needed the water it needed.
Ah, okay. So the next step is making the demand flexible too.
Exactly. They suggested exploring demand-side management, or DSM, looking at the copper production process itself, things like the huge grinding mills or the smelting process. Can those operations become more flexible?
Like, could they ramp up operations when solar power is super cheap and abundant and maybe dial back a bit during peak times or when the sun isn't shining?
Precisely. If you can make the big energy-using parts of the mine operate more flexibly, you could potentially unlock even more system efficiencies and cost savings beyond just optimizing the energy supply. It's sort of the next frontier in this integrated planning.
Makes sense. Integrating the demand side with the now flexible supply side. Okay, let's recap this deep dive then. The core takeaway from this research seems to be that fully renewable, zero freshwater copper production isn't just a dream. It looks economically viable now, thanks to this integrated planning approach, and particularly this IPHRO concept, the integrated pumped hydro reverse osmosis.
That's the key finding. And just to state the full title again for everyone, Integration of Seawater Pumped Storage and Desalination in Multi-Energy Systems Planning, the case of copper as a key material for the energy transition.
Right, so here's the final thought for you, our listener, to consider. If this study shows that the supply of clean energy and water can actually be cheaper and more stable, what does that mean for the industry? It feels like the pressure is now on the demand side within mining operations. The challenge is to accelerate the electrification or maybe the hydrogenization of things like haul trucks and smelting processes so they can fully sync up with and benefit from these low-cost, clean, flexible energy systems. The supply solution looks ready. Now the demand side needs to adapt to capture those benefits.